very quickly, we want to build a solar pumped laser. And there are many challenges in front of us. But as a material scientist, I will not be involved in the design of the laser, but I'm interested in the material. Other people will work on the design, of course. I'm interested in the material. From my perspective, what I see as the challenges for the lasing material are how to concentrate the solar light without using lenses or mirrors, but using these natural or artificial antennas that are something that collects light from sun and collapse everything in a single excited state, basically. This is the beauty of these objects. And then there is the other step, which is transferring this energy, which is being collected to the lasing unit. And the lasing unit can be molecules, can be nanocrystal, we will see. All these two processes, well, let's go this way. All these two processes require intermolecular interactions. So the thread that goes through my talk are intermolecular interactions. And actually, there are two kinds of interaction. Most of my talk, I will discuss about phenomena which are related to electrostatic intermolecular interactions. And the banner here just will appear sometimes to remind you we are talking about electrostatic interactions. Then there are other possible interactions, those are related to the overlap between the frontier orbitals. And I will just talk a little bit about these kind of interactions to discuss basically Dexter energy transfer. The main difference between the two is the distance where they occur. Electrostatic intermolecular interaction occurs when the intermolecular distances are larger than these 3 or 4 Armstrong, while for overlap between frontier orbitals, you need much shorter distances. I don't know why it disappears, but okay. What are the phenomena we will discuss? I will mention just briefly solvatochromism. So solvatochromism is, well, when you look at a molecule, at the dye, usually we are interested in dyes, dye molecules, so molecules that basically absorb invisible. We do not work with the molecule in the free space, gas phase molecule. We work with molecule in a solution or in a matrix in an environment. And typically, we think that the environment is very different from the molecule itself. And so usually you think of the environment as an innocent medium. I want to show you or convince you that the environment is not so innocent as we should hope. Then on the other extreme, we have the phenomenon which is called the system, which are called molecular aggregates. In this system, you have equivalent molecules that interact together. So now each molecule interacts with other molecules which are of the same kind. In between the you have what is resonant energy transfer. So you have similar molecule with, let's say, sort of similar absorption or fluorescence spectra. But in this case, we do not have energy delocalization, as in this case here, but we have energy transfer from one dye to another dye. So these are the 3 topics for electrostatic intermolecular interaction. As for going beyond electrostatic intermolecular interaction, so we have to account for possibility of electrons to transfer from one molecule to a nearby molecule. There are 2 phenomena. Davide is working a lot on this aggregate of scoring dyes, where charge transfer interactions are extremely important, but I will not talk about that because it is not so relevant to our project. Rather, I will try to introduce Dexter energy transfer. You already have seen this picture from the previous talk, because Dexter energy transfer is extremely important for, so if you want to transfer energy to nanocrystals. So let's start with solvatochromism. This is a very well-known dye. It's called Nile red. You can buy. It is very well known. It is called Nile red, but if you dissolve this dye, the same molecule in different solvent that go from cyclohexane, I guess, the yellow, to dimethyl sulfoxide, the blue solution, you see the color of the solution changes a lot. The molecule, the dye, the chromophore, call it as you want, is exactly the same, but the color of the solution changes with the solvent polarity. And of course, if the color of the solution changes, the spectra change a lot. When you go from hexane to dimethyl sulfoxide, the spectra move to the red, the absorption spectra of the continuous line. The dashed spectra is the fluorescence spectrum, always moves to the red as well. The reason for that is very well known. It goes back to a Sager model, so on Sager. So the idea is that if you have a polar, I'm not able to make this work, but I'm tall enough. If you have a polar dye, like this one, the polar solvent molecule that are represented as this little arrow. Okay, it was switched off, you know. The small arrow are a representation of the solvent molecule. They partially reorient around the solute, and so at the solute location, you obtain an electric field, which is called the reaction field. And of course, the reaction field is proportional to the dipole moment of the molecule and depends on the polarity of your solvent. The more polar the solvent, the bigger is this field.
You might be able to change that.
Now I can also do that. Thank you. Now, what happens when you go from a non-polar medium, where you have your molecule that absorb energy, of course, from the ground to the excited state. But now, when you go to a polar medium, both the ground and the excited state of the molecule are stabilized due to the presence of this reaction field, but the amount of the stabilization depends on the permanent dipole moment of the ground and of the excited state. In high red, the excited state dipole moment is much larger than the ground state dipole moment, and as a result, the excited state is more stabilized than the ground state, and you get a red shift on the spectrum. Okay, very easy, but there are other things to discuss about solvatochromism, but this is enough for today. I wanted to show you this because, again, we will see in a while why it is important. Now, I can go this way. Sorry. Now to molecular aggregate, the second topic. This is, let's say, the historical picture of aggregates. It is Scheibe, a German scientist. In 1938, he was able to demonstrate these aggregation phenomena. So the molecule is this molecule here, is one of the big family of cyanine dyes. We will see this cyanine dye so many times. We already have seen cyanine dyes in this slide on energy transfer or sensitization of non-crystals. In ethanol, which is a good solvent for this dye, you have the spectrum of the molecule. But if you aggregate this dye in water, you get this huge peak to the red with respect to the monomer. This is centimeter to the -1, so this is to the red. Very sharp absorption and intense absorption peak. So what's going on? I want to show you that this is not unique case. This is something that we measured in our lab. So this is another cyanine dye, very similar to the previous one. The main difference is the presence of this very long alkylic chain that just help aggregation. We have two dyes, this one and this one. You see, the main difference here is that the conjugated chain is longer here than that, but in any case, it is two dyes. In ethanol, both dyes are well dissolved, so these are the absorption and fluorescence spectra, nothing very special. Now we add water to ethanol, and the system aggregates. And now you see this DII has an absorption peak to the red, so something similar to what Scheibe showed many years back. And the system also fluoresces quite strongly. The other system has a completely different behavior, because when you aggregate, you see a peak that shows up in the blue. And in this aggregate, you have strongly suppressed fluorescence, something basically you cannot measure, not even measure. So can we understand this? Of course we can. The theory is pretty old. It is due to Kasha or Davidov, depending if you like an American or a Russian scientist. But it's very simple, or can be maintained very simple. So you consider a monomer, so the isolated molecule, the well-solvated molecule, where you have a ground and an excited state. Nothing very special, and this in transition frequency, of course. Then if you have a dimer, what happens? Instead of having two states, you end up with 4 states. Of course, you can have both molecules in the ground state, either one of the 2 molecules in the excited state, or both molecules excited. This is the case of non-interacting molecules. So if you shine light, you have 2 absorption. You go from here to there, and nothing very special. The only thing is that you have 2 absorption instead of 1, so the intensity of the absorption is twice the absorption of the monomer, simply because you have 2 molecules, nothing very special. But now, what happens if the molecules are close enough as to interact by electrostatic interaction? So, of course, if these 2 degenerate states interact, you get a splitting. Sorry. There is an approximation to be done here, because, of course, all the states of the 4 states interact. But the idea is that the interaction, the electrostatic interaction between the 2 molecules is small enough so that it is only relevant for the degenerate state. So it is simple perturbation theory. States which are very far apart do not interact strongly, or are not strongly affected by the interaction, to be more precise. So this is called the Adler-London approximation. So we will only account for the interaction between the 2 degenerate states. And of course, if two degenerate states interact, you get a splitting, and the amount of splitting is twice the interaction. Now, the point is, what it is the interaction, of course, is the matrix element between the two degenerate states. And now V is the electrostatic interaction, and in the simplest approximation, we stick on the dipolar approximation. And so J, this interaction, is proportional to the transition dipole moment between the two molecules. So basically, the interaction is the interaction between the oscillating dipole, the transition dipole moment of the two molecules. This is the main point. And of course, the interaction goes with the inverse of the R to the cube, the distance between the molecules. Now, we can elaborate a little further. Again, now we just consider the non-interacting molecule, the two degenerate state, and now they split. And of course, if you have two equivalent states, they split as the in-phase and out-of-phase combination of the original state. If this is the orientation of the dipoles, the energy of the in-phase combination is lower than the energy of the out-of-phase combination. And this is extremely important because in spectroscopy, only the in-phase combination of the two transition dipole moment gives rise to a global transition dipole moment. So the point is that in this case, you only see the absorption to the lowest energy state. This transition, the green, this one, is forbidden. So basically, you start from a monomer that absorbs here, and you end up with a red-shifted absorption. The important point, which is called the J aggregate, okay? The important point for us, Apache people, is that the intensity associated to the two molecules, so the oscillator strength associated to the two molecules, collapses down in a single state that then is strongly absorbing, and we are happy with that, but it is also strongly emitting. So this will be something that Luca will discuss as hyperluminescence or super radiant case. We can have a different geometry. If we are in this other geometry, of course, again, we have the splitting, but the order of the state is opposite because now we have repulsive interaction. And so now it is the state to the blue, which is the one which is seen in absorption. So we have what is called the H aggregate, blue shifted absorption. And because of the Kasha rule, this is a very big difference with respect to nanocrystal. In molecules, typically, the excited state relaxes very, very quickly, say 100 femtosecond, to the lowest excited state, to the lowest singlet, basically. And so basically, this state is optically active in absorption, but you will never see emission from this state because it lives too shortly. And so emission could only occur from this state, but this state has no transition dipole moment. And so H aggregate have suppressed emission, which explains the picture I showed you before. So these are J aggregate, fluorescent. These are H aggregate, non-fluorescent, okay? Well, two molecules versus many molecules. We don't know if in our solution we have a dimer. Most probably we have a larger aggregate. Actually, nothing much changes. Okay, there is some change, but I want to say the most simplest explanation. So what happens when you have several degenerate states, because you have several molecules, and so you can excite each one of these molecules. When they interact, you generate a band, and the width of the band is 2J, twice the interaction. When you go in the different geometry, the only things that changes is the curvature, say, of the band. And, but the point is that in optical spectroscopy, only the in-phase combination of the transition dipole moment gives rise to absorption. So here you have, again, red-shifted absorption and the fluorescent state. So again, J aggregate. And in the other situation, in this kind of geometry, you have blue-shifted absorption and no fluorescence because the system, when it reaches here, collapses very rapidly there. And so you don't have any emission in this case. Of course, a molecule need not to be aligned. The aligned molecule is the simplest system, of course, so just to illustrate the physics. If you have non-aligned molecule, again, if it is a dimer, you still have the splitting of the state. But look at the red curve here, or there, or here, it is the same. What happens, this is the absorption, the red curve is the absorption. What happens is that since you never have cancellation of the two dipole moment, because either the sum of the difference is different from zero, you see both absorption, both to the red and to the blue, with different intensity that depends specifically on how the molecule aggregate. There is another detail which is interesting here. This kind of aggregate can be chiral. And since they are chiral, you can measure what we call circular dichroism spectra. So this blue is circular dichroism. It is just a sketch of circular dichroism. The point is that since these are chiral, they absorb circularly polarized light with different coefficients depending if the light is right or left-handed. But okay, this is a sort of detail, but I wanted to show this to you because we have learned that natural antennas are chiral, and also some of the artificial antennas are chiral. Okay, which are the aggregates we are interested in Apache. These are the aggregates. The expert here are the people in Florence. Sandra, okay, and Mariangela, who is not here now. So again, cyanide dye, they form beautiful tubes. Sandra will explain this later on more carefully, but again, you see we have monomer absorption emission spectra and redshifted, strongly redshifted, very intense, very narrow absorption and fluorescence band. So again, these are J aggregate. We are able to collect all light in a single spot. In our lab, we have worked with a very, very similar system, and I know that you're interested to buy also these kind of molecules. They also form tubes and bundles, and again, we go from monomer to aggregate, again, J aggregate. Just to show you, these are also chiral, and just to show you, we can also simulate the spectra, but this is very easy. The other kind of aggregate we are interested in are the chromatophores from Massimo Trotta, and these are enormously complicated, a complex system. You see this is more than 4,000 molecules, but Alessia was able to simulate the absorption spectra of this thing. Is that true? It's beautiful. So experimental and simulated data were a very, very good agreement. So something can be done. But these systems are even more complex because, as I hope Massimo will explain this much better than me, we have a lot of chlorophyll molecules, bacterial chlorophyll molecules, to be specific, and they form rings with 9 chlorophylls or rings with 18 chlorophylls. These are by themselves aggregate. And the point is that if light is absorbed by the 9 chlorophyll ring, it is transferred almost quantitatively to the 18 chlorophyll ring. And so we want to understand or simulate how this phenomenon occurs. But this is really complex. So I will discuss now resonant energy transfer, also called sometimes Forster energy transfer, starting from scratch, from very basic things. So I'm sorry for the expert in the audience, but okay, I will concentrate on these 2 molecules. We have already seen that when we were discussing aggregate. You know, when we buy a couple of molecules, then we want to do everything with the same species. And what we have done with this molecule, I put a color code just to be easy. We took some vesicle, some liposome or vesicle, whatever kind. It is not important what it is. It is just a way to keep the 2 dyes very close, nearby. Because if you put these 2 dyes in solution, they are too far apart, unless you use too concentrated solution. But if you put them on a vesicle, you can have them close enough to study energy transfer. And now I want to show you what happens. Now, these are the green, focus on absorption to start with. The green line, this thing here, is the absorption of the green species, DII, and the red is the absorption of the DID, okay? Nothing very special. If you put the 2 dyes on the same nearby, you get the absorption spectra, which is the black ones, which is basically the sum of the 2, so nothing very special. Now, you go and excite, you shine light on your system here, where basically the red dye does not absorb, and all absorption comes from the green species, from DII. And now you look at fluorescence. This would be the fluorescence of DII. The red one is the fluorescence of DID. And now you see that the black curve, the curve that you obtain upon exciting here this species, is comes basically from the DII. So we are shining light on the green species, but as soon as the green species is excited, it transfers energy to the acceptor, to DID. Okay? Is it convincing? Good. Can we understand what's going on? Of course we can. So this is just a sketch to say that we have a donor molecule, we call it an energy donor and an energy acceptor. So we excite this molecule. As I said before, there is this Kasha rule. Wherever we excite, this goes down very, very quickly to the lowest single state. This state now lives long enough. We have an oscillating dipole here. If nearby there is a molecule where there is the potential to excite an oscillating dipole with the same frequency as this one, you have resonant energy transfer, of course, or the transfer of an exchange of a virtual photon. Call it as you want.
But Anna, just
Yep.
in your example, if you go back, they were not at resonance because the emission and the absorption were different, right?
Yeah, the point is that...
yeah, it was working so well because it was not at resonance. It was lower in energy, right?
No, the point is, the point is that you must have a matching between the emission of the donor and the absorption of the acceptor.
Yeah,
This is the point.
No, I'm just saying here in the absorption they're different. So
Yes.
different energy.
Yeah,
And one is lower.
yeah,
The acceptor is lower in energy.
yeah,
And so the emission also is lower. And here you have transfer all the energy they absorb up at high energy,
yeah.
transfer to lower. Otherwise, if they were at resonance, you
Ah,
would have
okay,
both
yes,
emission,
yeah, sure.
right?
No,
Just if I-
no.
If I
Why?
have
Why?
resonance,
No.
They should share the energy, right?
No, because, well, this picture possibly is not good enough, but the point is that, let's say, this picture is not good enough, but the point is that the system emits from the black line here, the zero vibronic state. And this state here can be in resonance, say the light lines here, so the vibronic excited state can be in resonance with that. And so you transfer energy, you can transfer the total energy. This happens quite...
Maybe Luca is right when he says that excitation energy can also
go back transfer.
If the transition energies are very close.
Yeah, but it depends on, let's say, the Stokes shift, basically. But, okay.
On different
Yeah.
overlapping.
Okay. Now, can we estimate the rate of this process? Okay, this is the process we are interested in, from the excited donor to the excited acceptor, so the start is the excitation. The rate goes with the Fermi-Golden rule, so the ingredient are the interaction between the two states and the matching of the energies between the excitation of the donor and the excitation of the acceptor, because, again, energy transfer can only occur between the general state. So what we do, again, the dipolar approximation, so that, again, we get the interaction between transition dipole moments. And the other clever thing that Förster did, Förster is another German scientist, is to substitute this Dirac delta with the overlap. The overlap between the emission of the donor and the absorption of the acceptor. Because, of course, this region marks the region where this relation is more or less obeyed. And if you do these two approximations, you get the Förster rate. So the rate goes with the inverse of the 6th power of the intermolecular distance, because it is the square of this thing here. And again, there is the square transition dipole moment for the donor absorption and for the acceptor absorption, or acceptor emission, but the idea is that they are the same. This is beautiful because these things, this is a prefactor that only depends on the relative orientation of the two dipoles, nothing very special. The important part here is that almost everything can be taken from experiment. The transition dipole moment can be measured, as well as the overlap, of course. So we are happy. We are happy, this is very useful, but we know that there are a few drawbacks or a few things that we have to be careful about. The first caveat is solvatochromism, the things I was discussing before. Here, everything depends on the relative position of this emission and acceptor, emission and absorption. And if everything moves with the solvent, as we have seen before, we have to be very, very careful. So something can be, energy transfer may possibly work perfectly well in toluene and can be totally absent in dimethyl sulfoxide, okay? Second caveat, this is more delicate. Replacing the Dirac delta with an overlap is a very useful trick because it can be obtained from experiment, but in a way it's a dirty trick because, of course, we are when you substitute the Dirac delta with an overlap, you are, let's say, broadening the states, and this implies basically accounting for energy dissipation, energy relaxation. To be more clear, if we go back one moment, sorry. If we excite here and get emission somewhere to the red, this means that we are dissipating energy in the meantime. So there are slightly more elaborate way to do that. We did that a few years back on a very, very simple system, because otherwise it is almost impossible to do. So the idea is to take our donor-receptor system and put this into a thermal bath, something that can accept energy. And this led us to something beautiful, at least something that I love a lot. So these are the two potential energy surfaces for the excited donor or for the excited acceptor, okay, the two potential energy surfaces. What we did is to excite the system from the ground state to create a coherent state, and then we were able, sorry, I have to go here. We were able the trajectory. You see the system oscillate on the excited state potential energy surface, then it stops down in what we call the Kasha state, and then very slowly goes down. This is not, let's say, this is a simulation, okay? And okay, this can be done. We've done this 5 years back. Doing this on this system is almost impossible, I would say. But because, again, we are interested in transferring energy from this ring from this ring to the other ring, and this is the work that Julien, okay, Julien, I got it, together with Eric are doing, but it is a very complex job, okay? And now to the very last topic, Dexter energy transfer, and you know why we are interested on that, which is the problem with this, the guy before me, I do not remember the name, explained it very, very clearly. These beautiful nanocrystals that are so beautiful for lasing and for everything are very, very tiny extinction coefficient. So very, very tiny transition dipole moment in absorption, and this means that if you remember the Forster energy transfer, if this number is very, very small, the absorption coefficient for the acceptor, for the nanocrystal is too small, of course you never have efficient Forster energy transfer. This is the issue. So the idea is to go with another mechanism, a mechanism that this time involves the overlap between the frontier orbitals. And of course, if you have an excited donor, you can imagine to transfer the excitation to the acceptor by a concerted transfer of two electrons, one from here, the other from there, and magically you go from D star to A star, okay? Which is the point. Now, the frontier overlap of the object that interact must overlap, and this means that the distances are very important because the overlap goes with the exponential, decays exponentially with the distance, okay? And actually, there are other mechanisms. So this is a beautiful review that I've seen recently. And you can go with this Dexter energy transfer, transferring simultaneously two electrons, or you can go transferring an electron and then an hole, or an hole and then an electron, going through this charge transfer state. But my point is that whatever it is, the mechanism, the rate of the process is always governed by the Fermi-Golden rule. And so again, what you have here are the interaction between the two species. But now it is not easy to calculate or get an estimate of this thing, because you have to know how the molecular orbitals are, how they overlap, so you need a lot of information, of detailed, very detailed information that is difficult to obtain for molecules, and for nanocrystal, in my view, at least, I'm not an expert on nanocrystal, but it is really a nightmare. The other point I want to make is that, again, we need a matching of the energies, otherwise, or at least a quasi-matching of the energies. But here it is very difficult, because in Forster energy transfer, the relevant state are optically active, so you know where the system absorbs and where the system fluoresces. In Dexter energy transfer can occur from single state, from triplet state, it can go to states which are optically active or not. So how can we know if there is this energy matching? And how can we optimize this phenomenon if we don't know where the states are? So it is really very difficult. And my point here to the Apache community is that what we need in this respect is a lot of experimental data. A lot of experimental data.
Where are the simulation people here? They just tell us to go back to the lab.
Or
This is what you actually
Obviously asking me, we want data.
maybe I'm not clever enough, but it is very difficult to sort out these things. From my perspective, it is very, very difficult. So Forster is easy in a way. You can go to basic experiment and get an idea. Here, dark states are involved. In Florence, people can do measurement to see where dark states are, but not easy. It is non-trivial, okay? Okay, so with this is my last slide. No conclusion. A lot of problems, very few solutions for now, but I'm confident that together we will manage.